Alright everyone, so this is going to be the final video that we're going to do on things that we actually need for Calc 1. Um, the last one was kind of long, this one will be pretty short. We're just going to wrap up a couple of things, talk about a couple of shortcuts for some integrals, one nice thing we can do with them, and then give a very, very brief kind of description of some things you can do with integrals for differential equations. Okay, so the major things we had from last time was the fundamental theorem of calculus part 1 and also part 2. So we had this area function a of x, which we said was the area, the net area underneath f of x or f of t, whatever variable you want to use, from a to x. And then we said that the derivative of that area function was just the original function we started with. Right, so what this says is that the derivative of an antiderivative is the function you started with. And then we said that we could go and take the definite integral of a derivative and get f of b minus f of a. So we're taking the antiderivative of a derivative and we're getting a slight twist. We're not exactly getting the original thing back, but we're getting the original thing evaluated at the two endpoints. We're getting the f of b minus f of a. Okay, and then we might remember something that we'd said about symmetry. I don't know, getting 3 weeks ago or so. So we said that a function has even symmetry if you can fold it across the y-axis, and odd symmetry if you take it around the origin, rotate 180 degrees, and you get the same thing. So something like sine of x has odd symmetry, and then something like cosine would have even symmetry. So some rules for doing integrals with even and odd symmetric functions. So the first is that if you're taking any odd function you like and you integrate it from minus a to a, where a is some number, that integral is always 0. And the reason for that is kind of straightforward from the picture. So if we go over here to some point on the positive side of the x-axis, so say I go over to pi, and I go and I look over here at minus pi. Well, each of the positive parts, every positive bit over here is being canceled out by some negative part on the negative side of the x-axis. So what this says is that if I went over to minus pi to 0, what I'd wind up with is the exact negative amount of area as when we go from 0 to pi. Okay, well, an even function like cosine. Well, what we just said was that for odd functions, when we go from minus a to a, we're going to get 0. Here we're going to get is, well, we're not going to get 0. What we're going to get is twice the area from 1/2 of this. So pictorially, here's what we've got. We have cosine, and we'll go from, say, minus pi over 2 to pi over 2. Well, the area over here, from minus pi over 2 to 0 is the exact same as the area from 0 to pi over 2. So what we can do is go and collapse the area from minus a to a as twice the area from 0 to a. And this is one kind of typical test question that you'll get, particularly for a final, is we'll ask you to do something like find the integral of some function, making use of geometry or symmetry. So, standard kind of test question that we give for finals. Okay, so a couple of examples of these. So let's go and find the definite integral from minus 3 to 3 of 3x squared minus 7x dx. And then we'll come back and we'll do a second example, so minus pi over 2 to pi over 2 of sine plus cosine. So for the first example, what we can do is we can split our function into two different integrals, one from minus 3 to 3 of 3x squared, and then another one, so we'll subtract off the integral from minus 3 to 3 of 7x dx. The second integral is going to be an odd function. We have only odd powers of x, so that integral will be 0. The first integral, we have an even function, so we can take twice the integral from 0 to 3 of x squared, and when we find that, we wind up with 54. For the second one, we're going to do the same kind of thing. We have an even function in cosine, we have an odd function in sine. We'll go and write our integral as the integral of cosine plus the integral of sine from minus pi over 2 to pi over 2. The sine integral is again going to give us 0 because of the odd symmetry. And the cosine integral we can take as twice the integral from 0 to pi over 2 of cosine of x. We find our antiderivative is 2 sine of x, and we'll evaluate at x equals pi over 2, subtract it off at x equals 0. And when we do that, we get 2. Okay, so then we can talk about the average value for a function. Right, so we had this plot from the last time, and maybe now what we'd like to do is find the average value that this function takes on over the intervals 0 to 1. Well, this kind of seems strange for a function, but if we were doing it for just a couple of values, this would make more sense. So for example, I have this picture, but say that we had 3 people get together and we wanted to see the average amount of money they had. One person has $50, the other one has $25, and the third person has $5. No, I'll make the third person have 15. So the first person has 50, second one has 25, third one has 15. Well, how would we find the average amount of money that these people have? Well, we would just add up the money that they have and divide by the number of people. So we would add up 50 plus 25 plus 15, that adds up to 90. We'd divide it by 3 and we would say, oh, the average amount of money that these people have is 30. Well, another way that we could do this is we could say, well, let's go and draw a plot of what's going on here, and we'll look at areas of rectangles. So one, we would give an area, or we'd give a width of 1, a height of 50 for our first person that had $50. The second one will give a width of 1 and a height of 25 for our second person with $25. And lastly, we would go and take a width of 1 and a height of 15. And then what we could do is add up the areas of the rectangles that we have here and then just divide by, well, incidentally, the number of rectangles, but really the size of the interval. So we can do exactly that here. So if we wanted to find the average value, we could go and approximate the area and then divide by the size of the interval. And in general, that's how we find the average value. So to find the average value of a function, we take the expression 1 over b minus a times the integral from a to b of f of x dx. What this is saying is that we have this definite integral, which is giving us the net area for f of x over the interval a to b, and then we have this f bar b and the b minus a. What this is saying is that we could go and look over the same interval, and we could come up with a rectangle that has the same area, same net area as the function over this interval of b to a. And what you're trying to find is what is the height of the rectangle that will have the same area as our function over the same interval. That height's going to be f bar. The width of your rectangle would be b minus a. Okay, so we had a mean value theorem for derivatives, and we also have a mean value theorem for integrals. So if we start off with a continuous function on the interval a to b, there will be some c in between a and b, so that f of c is going to be this average value. So what we'd like to do is just do an example of that. So let's find the average value for f of x is x plus 2 over the interval 0 to 4, and then we'll find the c that so that f of c is the average value. Okay, so the first thing that we'll do is we'll go about finding what the average value is. So we'll take this expression 1 over b minus a times the definite integral from a to b of f of x, plug in our a, b, and f of x, and after we evaluate the integral, we get 1/4 times the quantity x squared over 2 plus 2x, evaluated at x equals 4 and 0. When we evaluate this at x equals 4 and simplify, we wind up with 4. So the average value for this function is 4. So again, if you wanted to draw a rectangle over the interval 0 to 4 that had the same area as our function over the interval 0 to 4, you would go and put the height at 4. And now we want to find the c so that f of c equals 4. So we'll set f of c equal to 4, and solving for c we get 2. Okay, so to recap, we have a couple of these rules that we saw last time for integrals. So one was that if we have an integral of e to the ax dx, we get e to the ax divided by a plus our arbitrary constant. If you're trying to find the integral from a to a of f of x, that's 0. We can flip the bounds around on our integral by putting a minus sign out in front. We can split integrals apart, so the integral of the sum, so f plus g, is the sum of the integrals, so integral of f plus integral of g. We can pull constants out in front, and we can divide up an interval as we need to. So the integral from a to b of f is the integral from a to c of f plus the integral from c to b. Okay, so if we're given a velocity function, we could find the net displacement, so the difference in the starting point and ending point, by integrating v from a to b. So that'll give you the difference between where you finish and where you started. And if you want to find the total distance traveled, you'd need to find the integral of the absolute value of v. So what the absolute value part would be giving you is, it wouldn't concern whether or not you're heading in the positive direction or the negative direction. It would just go and sum up all of the distance traveled. So we'll go and do one example of how we could find the displacement and then also the total distance. Okay, so first we want to find the displacement of an object that moves with velocity 2t squared minus 8t plus 6 from t going between 0 and 3. Okay, so this net displacement, so p of b minus p of a, it's given by this integral from a to b of v of t, so we'll just integrate v from 0 to 3. We get our antiderivative to be 2t cubed over 3 minus 8t squared over 2 plus 6t, evaluate at t equals 3, t equals 0, and when we do that, we wind up with 0. So what that says is that the object has started and ended at the same place. However, if we want to find the total distance, we just need to do a little bit of manipulation first because of that absolute value. So we can observe that v is going to be negative for t in between 1 and 3, and it'll be positive otherwise. So to find the total distance traveled, we'll look at the integral from a to b of the absolute value of t, and I'm going to split this up as the integral from 0 to 1 of the absolute value of t plus the integral from 1 to 3 of the absolute value of t. The reason for that is in between 1 and 3, v is negative. Between 0 and 1, v is going to be positive. So what that says is that our absolute value of 2t squared minus 4t plus 3 in between 0 and 1 is just going to be 2t squared minus 4t plus 3. For the other interval 1 to 3, remember that we'd said the absolute value of a negative number is minus that negative number. So you get minus a negative and get the positive number returned. So we're going to write the second integral as minus the integral from 1 to 3 of 2t squared minus 4t plus 3. And then again, we're going to go and evaluate these integrals. And after a little bit of algebra, what we see is that the integral evaluates to 16/3. So what that says is that our object moved a total of 16/3 units, so meters, feet, whatever, but went 8/3 out and then 8/3 back. So started and ended at the same place, but did actually move somewhere. Okay, so the final thing that we need to talk about here. So suppose we wanted to recover the position function, we'll say. So we know that the difference between the start and the end is found by p of b minus p of a. It's equal to this integral from a to b of v of t. So if we wanted to find the position function in general, and we started with p of 0, we could go and say that p of t is equal to p of 0 plus the integral from 0 to t of v of x dx. And we could do the same thing if we had accelerations and velocities. So here what we're going to do is we're going to go and find the population as a function of time based on the initial population and also the rate of change of that population, so the p prime. Okay, so what we'll do is we'll just go and put our capital P prime into this expression where we have a v, and then we'll use p of 0 equal to 100. So we can find the population as a function of time equal to the initial population plus the integral from 0 to t of p prime of x dx. Our rate of change for the population is 90 e to the minus 0.1x. And from that rule that we had for doing exponential, integrals for exponentials, we'll get that the function is 90 over 0.1 e to the minus 0.1x, and we're going to evaluate this expression at t and x equals 0. And then doing that, we'll get 100 minus 900 e to the minus 0.1t minus 900 e to the 0. So we get 100 plus 900 for 1,000 minus 900 e to the minus 0.1t. And that's what we would get for the population function. Okay, so that's everything that we need to say for Calc 1. As I said, I'm going to do 2 more videos that are going to give you an introduction to some of the things you see in Calc 2. And I will see you all then.